We're rolling back the clock a little bit here today, and this topic is called further functions. It actually sits in chapter 7 in our textbook. And so given that we've just knocked over chapter 11, we're going back in time and further back even than calculus. Okay, so today we're going to look at something called more power functions, but some of the concepts that are explored here relate to odd and even functions. So I'm going to quickly talk about odd and even functions again. So a function is odd, so it's classified as an odd function if, when you reflect it in the y-axis, it's the same as the reflection in the x-axis. And this has to be true for all x in the domain. Okay, so I'll explain why for all x shortly. But another one we can do is we can test if it's odd by rotating the function 180 about the origin. All right, let's go with the first one here, and let's take this graph here, which is based on y equals sine x. Now, what you'll note here is that if I reflect it in the y-axis, what will happen is this part here will become this part here. This part here will become this part here. Now, over to this part. So this part here, that part, will become that part. This part will become this part. And you notice here what I've produced is that graph there. And I might change color just to emphasize this. Let's go with a fluoro green just to be really emphatic. So that's what I've got. And you can see here that it's just going to continue for all x. And again, if you sort of said or noted, what's the relationship between the green function and the red function? Well, the green function is simply a reflection of the red function in the x-axis. Okay, so we can conclude here that y equals sine x is odd because when it's reflected in the y-axis, it yields the same result as reflecting in the x-axis. The second one is a different test that you can do. So you can do one or both of these to check for whether a function is odd or not. So I'll just draw y equals sine x. What I'll do is whack a point at the origin. And I'm going to use a reflection around a point, or rotate rather around a point. So this function rotating around that point. And what I'm going to do is rotate 180 degrees. Now, if what happens is that I return the exact same function, so if after rotating 180 about the origin, I return the same function, we can also conclude that we've got an odd function. And it did, okay? So notice that no new function was produced there, and the reason for that is, like if I take away the original function, what we can see is the function underneath it is exactly the same. So when I rotate this 180 about the origin, I get the same function in return. So we can conclude that y equals sine x is odd because when you reflect in the y, it's the same as reflecting in the x, but also because it has this property that a rotation 180 about the origin produces the same function in return. All right, a function is even if you reflect it in the y-axis and it's the same as the original function. Okay, so parabolas have that property. So if you reflect y equals x squared in the y-axis, you just get y equals x squared. Right, and this is another function that has this property. So this graph here is y equals cosine x over, what's the domain? That's just the standard cosine, 2 pi, over the period 2 pi. So what we'll note here is that when I reflect this part here, it'll become that part. That part will become that part. And in essence, we're just saying that a reflection in the y-axis does nothing. It returns the same function. Okay, so we can classify that as an even function. Okay, so y equals cosine x is an even function. And for the same reason then, we can say y equals cosine negative x is the same as y equals cosine x. Right, so that's an important property for cosine. Just the same as if I said here y equals sine negative x, I can rewrite that as y equals negative sine x. Okay, I've seen that property come into play in exams before, so it's worth just keeping that on the radar. All right, so let's explore some functions. So what we're going to do is explore the power function where we've got f of x equals x to the power of negative 1 over n. And n is a positive integer, so it's a value like 1, 2, 3, 4, dot, dot, dot. So that can also be said as z positive. All right, now to kind of try and picture what's happening or the function behavior, I'd get it out of this form. Negative indices are not great at allowing us to get an idea of what it might look like. So if I write it as 1 over x to the power of 1 on n and 1 over the nth root of x, what that allows me to do is visualize it a little bit better. So I've got two examples that appear right. Okay, so this one here is 1 over the third root of x. Okay, so what it does, you'll note, is it looks very much like a hyperbola. So we've got asymptotic behavior along here and along here. All right, so this vertical asymptote here is obviously because 1 over 0 is undefined. Okay, and as x increases, what we're going to do is nth root whatever the value of x is, which will always produce a value. You're never going to actually be able to touch 0. Now, why the domain? So it says the maximal domain is the set of all real numbers except for 0 if n is odd. Okay, so when n is odd, i.e. third root, fifth root, seventh root, what we're going to do is get something that looks like this, okay, with a domain set of all real numbers not including 0. Now, to understand why that occurs, you need to go back to the third root function. So let's just quickly review that one, third root of x. Okay, so the third root of x function is very similar to the second root of x function. So it produces a graph that looks like that. The only difference is, remember that you can third root a negative number, so it produces that down below. All right, and then what happens is the extended function that we're doing is we're doing 1 over, so y equals 1 over the third root of x here, okay? So what it does when you do it, you go 1 divided by this value, and it twists the numbers. Basically, it just grabs this arm here and turns it into a hyperbola, grabs this arm here and turns it into like the left-hand side of the hyperbola, okay? So that's how to pick sort of the function behavior. Now, the maximal domain is all real positives if n is even. Now, why is that the case? Well, note that the standard root function, so square root, fourth root, sixth root, any even root will look something like this. And you can't get values over this side of x, the negative values of x, because these numbers are not defined for a even root function, okay? So you can't square root a negative number, basically. You can't fourth root a negative number, okay? So what we're going to do is take that function, so that's y equals the second root of x, and then to twist it into this, we just go y equals 1 over the second root of x, which creates a right-hand side of the hyperbola, but it can't produce the left-hand side because it's not defined there. So that's why there's a difference between when n is odd or even. So we're going to go say something like this. Third root x is defined for all x. Second root x is defined for 0 up to positive infinity. All right, so let's have a look. If n is an odd positive integer, i.e. n is equal to 3, explain why it's an odd function. Okay, so let's consider it. So f of x equals x to the power of negative 1 over 3, which is equal to 1 over x to the 1/3, which is 1 over the third root of x. All right, now why is this an odd function? Well, if you have a look at the graph itself, all right, so this red graph, is it? Yeah, the red graph is the third root function. What you'll note is if you rotate this 180 degrees about the origin, so you go that part goes to that part and then that part, and then you go one more rotation, you basically are going to return the same graph, okay? So we're going to say here, this is one way of doing it, we're going to say a rotation 180 degrees about the origin returns the same graph. Therefore, it is an odd function. The other way you could do this is you could do f negative x and show that if you do f negative x, that what you're going to get is a reflection in the x-axis. So remember, with odd functions, it has the property that reflections in the y-axis are the same as reflections in the x-axis. Let's explore that with this. So f negative x equals, so let's bang it into here. So we're going to say that we've got 1 over, and I'm going to bang it into this version of it here, 1 over, not x, I'm going to put negative x in, to the 1/3. Now that is going to be negative 1 times x all to the 1/3. Watch your vinculum there, make sure it covers the whole thing. And that is going to be, so negative 1 to the 1/3 is going to be negative 1. So this is going to be 1 over negative 1 times x to the 1/3, which is negative 1 over x to the 1/3. Okay, and so what you can see is when I put negative x in, or reflect in the y-axis, we can actually rewrite it algebraically with the negative sign here, which, if you recall, that's just a reflection in the x-axis. It's negating the function. Okay, so it's exactly the same thing. So what we can conclude then is, therefore, reflection in y is the same as reflection in x, therefore odd. Okay, so we've used the two ways to explain why it's an odd function. We've talked about the graph itself, okay, and then we've done it algebraically using that property. Okay, using the graphs of f of x equals 1 over root x, explain why it's neither odd nor even. So we've got to use the graphs this time. So here is 1 over root x, and what we're going to do is we're going to reflect in y. What do we get? We get that. So when I reflect it in y, I get that, which is not the same as original, therefore not even. Okay, so remember, an even function has the property that when you reflect it in the y-axis, you get the exact same function in return. And like if I said that and that are the same, you'd be like, no, they're not, and you'd be right. Okay, let's go with odd. So here is my original function. That's y equals, so that's f of x there, and that's f of x. And what we're going to do is I'm going to rotate it 180 about the origin. So 180 about origin, and what that's going to produce is that function there. Okay, so remember, what I do is I imagine putting like a thumbtack in there and then just turning my paper 180 degrees, so flipping my paper. So that will go to there after 90 and there after 180, okay? And same conclusion, which is not the same as original, therefore not odd. So we call that function neither odd nor even. All right, use your calculator to help you sketch the following graphs. State the maximal domain and the corresponding range. All right, so let's just try and do as much as we can without the calculator and see how we go. So I'm going to rewrite f of x as f of x equals 4 over the 4th root of x, take 2. All right, now what's this going to do? So we're going to get hyperbolic behavior, all right? So that's one, like this would be like 1 over x. So it's going to be sort of hyperbolic behavior, but because we're 4th rooting x, it's going to mean that the only values we can 4th root are 0 to positive infinity. Now what this negative 2 will do is move it 2 units down. So we're going to grab that horizontal asymptote and we're going to move it down 2 units. That's y equals negative 2. Our vertical asymptote stays exactly the same. So that's x is equal to 0. So what's going to happen is we're going to get a function that looks like this. Okay, so the x-intercept will be something over here. So x-intercept occurs when y is equal to 0. So 0 equals 4 over x to the quarter. Take 2. 2 equals 4 over x to the quarter. Now I'm going to swap that. So x to the quarter equals 2. Okay, now what value of x when fourth rooted will give me 2, or raise that to the 4, raise that to the 4. That's going to be x equals 2 to the 4 is equal to 16. So x-intercept is 16, 0, and our graph is going to look something like that. Right, so no real need for the calculator on that. State the maximal domain. So domain of function is 0. Whoops, can we include 0? No, we can't. Okay, because we can't divide by 0 there. So 0 to positive infinity. Range of function is going to be -2, but it's asymptotic there all the way to positive infinity. All right, so didn't need a calculator for that one. All right, let's try this one here. So we're going to rewrite it to try and visualize it. So 2 over x to the 1/3 plus 1, or 2 over the third root of x plus 1. So what we're going to get is hyperbolic behavior for this part here, plus 1. The plus 1 is going to grab the horizontal asymptote and lift it up. So y equals 1, x equals 0. Okay, and so what's going to happen is it's going to look like that and like that. So we're going to get an x-intercept somewhere down here. All right, so let's concentrate on this side to get the shape, and then we're going to use symmetry to get this part of the, in inverted commas, hyperbola. All right, so now let's say that 0 equals 2 over x to the 1/3 plus 1. Now we're going to go -1 equals 2 over x to the 1/3. X to the 1/3 equals -2. All right, and then we'll power 3 that and power 3 that. X equals -8. Okay, so let's pop it in there, -8. All right, and that'll do nicely for that graph there. So we've got -8, 0 as our x-intercept, no y-intercept. Domain of function is all real numbers, but let's take 0 out of there. Range of function is all real numbers, but let's just yank 1 out of there. Right. The function f of x where p and q are positive integers. Okay, so what we can do is vary both p and q, and this is going to cause all sorts of crazy behavior. All right, so to explore these functions here, actually evaluating a problem like this from year 10 becomes really important. So evaluate 8 to the power of 2/3. Well, that's going to be the same as 8 to the 1/3 to the power of 2, and that's the third root of 8, which is 2 to the 2. 2 to the 2 is equal to 4. So that's a really important skill because it allows you to sort of predict what the function may look like. All right, so notice that if f of x equals 1 over q to the p, then that's the same thing there. What's the maximal domain going to be if q is odd? All right, so that means that we're either third rooting, fifth rooting, seventh rooting, ninth rooting, odd rooting x. Now, when I odd root a number, it's defined for all real numbers. So even if I raise it to the power of p, it's still going to give us a maximal domain of the set of all real numbers. Now, you should be using GeoGebra to play around with this as well. So I'd be actually setting up some scenarios on this one and just checking what the resulting graphs are. Now, the maximal domain, if q is even, so if q is even, that means we're second, fourth, sixth rooting. And what that means is we can only sixth root or fourth root or second root when the values of x for 0 to positive infinity, inclusive of 0. So if we raise that to the p, then 0 to the p, that's fine, that's all acceptable. So we're going to say that the maximal domain, if q is even, is going to be 0 to positive infinity. Now, Mr. Tench reckons that you'll always have your calculator if these questions are ever asked, okay? And think of a really good problem, multiple choice 2018 exam that required a good understanding of these kind of power functions here. All right, so here's two examples. So what we've got is the function f of x equals x to the 2/3. Now, why does it look like this? Well, let's consider it. F of x equals x to the 1/3 to the 2. Right, and what that basically does is it takes our 1/3 function, so x to the power of 1/3, and what it does is it just squares the values. Okay, so obviously it's going to make those values jump a little bit faster for these positive x values. 0 stays at 0. And these ones here, because it gets squared, basically will grab this negative side here and turn it into something like that. So you get this little thing here happening. I think that's called a cusp. I'm not sure, but I think that's what I've heard it called. Okay, so that's what results from that. And that sort of shape will happen for all functions like it. So like if you do 4 over, say, 7, you're going to get something cuspy, okay, something that looks like this. You're going to get for x is equal to 6 on 19. Okay, that's the behavior that you're going to get, because you're going to get x to the power of 1 over 19. Okay, so that's an odd root, and then you're raising it to an even power. Okay, so that behavior there will be familiar for all of these functions. All right, over here we're looking at f of x equals x to the 3 on 2, which is the same as x to the half to the power 3. Okay, and what that does is basically going to take the square root function, and those results there, it's going to power 3 the result. So it grabs these ones here, brings them up, brings them up, brings them up, and what it ends up doing is creating something that looks a little bit like the right-hand side of a parabola. Okay, now again, notice that the domain is going to be only true for 0 to positive infinity. Why? Well, it's all got to do with how you break it up and visualize the different parts. And you can't square root a negative number in maths methods. So you can square root 0, okay, so that's where it starts at 0, 0, okay, and it's true for all positive values, but it will not produce or accept values less than that because it breaches those conditions. So explore these functions, use your calculator, okay, and really practice trying to visualize them. Use GeoGebra a lot on this to try and visualize the functions, or not try and visualize, to get the actual visual on the function. These ones often come up in exam 2, so yeah, worth practicing.